In this video, which should be a pretty quick video, I'm going to talk about some initial Imagenette experiments that I've been running, what I was motivated by to run these experiments, and what my next steps are looking forward to try to get on the Imagenette leaderboard. So I'll start with the motivation for doing this, and then I'll talk into what exactly Imagenette is, and what my results are on my initial experiments, and what my next actions are. So this is all tied back to my TinyScaleLab project, where I'm trying to train good performance tiny language models while also studying their training dynamics and analyzing how they relate to downstream capabilities. This project was inspired by the Tiny Stories paper as well as the Small Scale Proxies paper. I have a whole playlist of my TinyScaleLab project on my YouTube channel, so check that out if you're interested. I was running these initial one epoch kind of quick and dirty runs on a 3090 GPU to try to understand what batch size should I use to kind of maximize training speed, so get the highest speed up I can while also getting the best training performance, roughly speaking, because I was just kind of throwing things at the wall right at this point, not really thinking about how I'm going to get the most out of the downstream performance at this point. So I tried 5 different batch sizes from 64, 256, 1024, 2048 to 4096. 4096 in my case through an out-of-memory error, so that's an easy way to discard that batch size. But I found something interesting, especially for the 1024 and 2048 batch sizes, where I found that I did not get a speed up even though I was doubling the batch size. That was the first discovery. The second thing I realized is that, relatively speaking, compared to 256 as a batch size, the train loss and eval loss is considerably worse when I, double or quadruple, or actually quadruple or 8x the batch size. These things were counterintuitive to me. I was asking Claude, and Claude said that, this makes sense, and it provided some explanations, which I'll get into in a second. But I was expecting that I could increase batch sizes and I could get a speed up. And then I was also expecting that a higher batch size would give me a lower final training loss because I was giving it a closer representation to the full data set. So as is the case for me when I usually run into something that's interesting or counterintuitive or surprising, I posted this on Twitter talking about how I had gotten this result where a high batch size was not more efficient, and I posted my weights and biases law to the post. And this gave me a lot of interesting replies that I'm going to go into, and that's going to be really the motivation for doing this Imagenette training experiments. So the first thing was from Jeremy, who said that this concept of batch size versus efficiency in training was covered in some of the earlier courses. Lower batch sizes provide more updates, which should give better results for a fixed number of epochs. So I had, for example, 4.9 million stories in the Tiny Stories dataset. If I'm going to go through one epoch, so I'm going to go through all 4.9 million stories. If I go 256 stories at a time, I'm going to have 4 times more the number of gradient updates compared to going through the entire epoch with a batch size of 1024. And for 256 compared to 2048, I'm going to have 8 times as many updates for my gradients going through the entire batch size of 4.9 million stories. So this, that made sense. This was actually similar to what Claude replied when I asked it this question about, how this was counterintuitive to me. Another reply from Benjamin Warner was that Tiny Stories is a pretty homogeneous data set, so one doesn't need as large of a batch size to achieve a smooth gradient compared to a more diverse pre-training set. You'll want to set the batch size balancing speed and performance. So the idea behind this is like, for something like the pets data set, for example, you have lots of different breeds of cats and dogs. You could imagine that a batch size of 32, you might get stuck in a situation where you have all of the same, cat breed in those 32 samples. Whereas if you expand your batch size to 256 or 512, you are guaranteeing, or more likely to guarantee, because it's not, a full guarantee because there's going to be some randomness, but it's more likely that your batch size of 256 or 512 will have a more diverse set of pet pictures that's more representative of the data set. So that was another idea here. Tiny Stories as a data set is relatively homogeneous because all 4.9 million dataset items are children's stories. The plot changes, the names change, the length might change a little bit, but in terms of content, it's exactly the same. There's no variation in the type of language that's being used. And then Radek, who's also a FastAI community member / alum, said that one heuristic that people use is that in most scenarios, you can scale the learning rate proportionally to the batch size. Larger batch size, better but less frequent updates can take longer steps. Smaller batch size, more frequent updates, but need to take smaller steps due to the worse direction of updates. So this was, again, related to what Jeremy had said about lower batch sizes provide more updates, which give better results. Larger batch size is better in terms of a smoother gradient, but it can take longer steps, so you have to train it for longer. So these are kind of the different variables, different levers that I have to pull. And going back to Benjamin's point, I want to set a batch size so I can balance speed and performance. And then the last one, which was really the motivator for this ImageNet experiment exploration, was that Jeremy said you should maybe try doing some ImageNet speed running. It's a good way to get an intuitive understanding of these issues. So that's what brings me to the ImageNet dataset, which is also a leaderboard. So if you go to github.com/fastai/ImageNet, you can read about the dataset, and then you can also see the leaderboard, which has the top 5 entries for each epoch and image size. So for example, they have a 5 epoch category, and then they have a 128 pixel image size, and then they have the top 5 accuracy values for the different entries that have been submitted. There is also a ImageNet tutorial on the FastAI docs, and it's called Training ImageNet, and it goes through a lot of interesting points about loading the data with a factory method, with the data block API, with the mid-level API. So it was a nice refresher on how to use the data block API, and then it goes through process, starting with a learner, changing the loss function, changing the optimizer, introducing a callback to change the training loop. So these were all like really awesome things for me to get a refresher on. So I highly recommend, if you're looking to do the ImageNet competition or leaderboard, then definitely do the Training ImageNet tutorial on the FastAI documentation. Okay, so what did I do for my initial 5 epoch training runs? Well, first of all, I chose 5 epochs because I want to do the quickest runs first. So I'm trying to see if I can get on that 5 epoch leaderboard for ImageNet. I chose a batch size of 64 just because it's the default that you have when you're using the factory data loaders method. And then for each of the models, I chose 3 models. For each of the models, I ran LR find, and I saw approximately which learning rates are reasonable. So I picked 1 ENEG 4, 1 ENEG 3, and 1 ENEG 2. And I did 10 runs, so 3 models with 3 learning rates. And for one of the models, XResNet 18, I also found that based on the LR find results, the 1 ENEG 1 learning rate was still stable. So I tried that as well. So I got a total of 10 runs and 10 final accuracies. And the top 3 were, interestingly, all for 1 ENEG 2. And then the next 3 were 1 ENEG 3. And then we had that 1 ENEG 1 for that XResNet 18. And the 3 worst performing accuracies were for training runs that used a 1 ENEG 4. So we had this hierarchy of 1 ENEG 2, 1 ENEG 3, and 1 ENEG 4 kind of naturally occurring for these training runs. Another interesting point is that my top 3 were all representative of each model. So I have my XResNet 34, I have my XSE ResNext 50, and then I have my XResNet 18. So interesting to see that the top 3 have all 3 models, which is good for me because now when I take on the next steps, I can just pick these top 3 and I can have each model represented in my future experiments. And then I guess the last interesting thing to note about these accuracies is that even though XResNet 18 has half the parameters, it was very competitive in terms of the accuracy. So that's something I'll be looking forward to see if that maintains at different batch sizes and learning rates and longer epochs and so on. I'm picking 3 of the training runs to highlight because they were unique in relation to the other 7, which were pretty similar in terms of how the accuracy curves were shaped across the training regime. The first one that I'm going to look at is the XSE ResNext 50 1eNeg2, which ended up with the second highest final accuracy. But interestingly, it started with the lowest accuracy after 1 epoch. So again, just interesting to see that what may happen at the early stages of training is not necessarily indicative of what's going to happen at the end of the training run. The second curve of interest is this XResNet 18 1eNeg1. This was the only curve where the accuracy dropped from 1 to 2 epochs, but then it picked up again and it finished in 7th place. And then the third curve of interest is the XResNet 34 1eNeg2. It had a relatively slow increase from 1 to 2 epochs, but then it had a significant jump from 2 to 3, and it actually ended up having the final highest accuracy out of all 10 runs. So just a few interesting things that I wanted to note from the accuracy curves. Okay, so with that under my belt, what are the next steps that I want to take? So one of the things that I want to highlight from what Jeremy said is just filling in a bunch of hyperparameter results isn't interesting. You actually need to try to win. And what he means is just try to get on this leaderboard. And it doesn't matter if you make it or not, but you'll see what actually leads to fast, accurate training. And maybe on the way, you'll want to create some tables like you're making there, but I rarely find them as interesting as small, targeted iterations changing one thing at a time. So I want to keep that as my main focus. I am obviously very interested to see how these different training runs vary based on hyperparameters, and I'm inclined initially to kind of just do these but I think what Jeremy's saying here, and also from my conversation with Claude, was that building intuition is different from just running a bunch of hyperparameter sweeps. So building intuition, I think, is going to be best done by doing these small targeted iterations, changing one thing at a time. So here's my next steps. First, I'm going to pick my top 3 models and vary the batch size and learning rate. So this was my original kind of curiosity, was understanding what is the relationship between batch size and training performance. Training time is not that important because Imagenette is so small that it takes like 10 to 30 seconds per epoch. But I'm really interested to see that for the 5 epoch fixed training regime, how does the final accuracy change as I vary the batch size and then as I vary the learning rate. And so, this is going back to my motivation slide, what Radek has said about the relationship between learning rate and batch size. I'm trying to see that visually through these training runs. And then when I move past the 5 epoch regime and go into the, I think 20, 80, and 200 are the other epoch regimes, I want to implement data augmentation. I want to maybe implement different losses. And then I also want to implement techniques from the fast extend and optimize libraries. So there's different optimizers, there's different techniques like progressive resizing that are easy to implement. And then fast extend has its own set of vision data augmentation as well that are different from the fastai data augmentation techniques. So these are my next steps, and I think this will give me some bite-sized experiments to iterate on quickly and hopefully start gaining some intuition on what works and what doesn't work. And again, just highlighting that these top 3 results for a batch size were for a batch size of 64. So I'm interested to see how that changes as the batch size increases. So I have linked my blog post that has all of the code in the video description below. So take a look at that if you're interested. I used most of the code straight from the training with Imagenette tutorial in the fastai docs, so you can just look at that as well. I'll post that in the video description as well. And I'll also put into the description the link to the Imagenette repository where you can look at the leaderboard results. So that's it for this video. Thanks for watching. Please like, comment, subscribe, and I'll see you next time.